In this video, we're going to discuss concavity and a few definitions and theorems related to that, and then we will start to see how this can be applied to sketching curves. So we're going to start with a definition here, and that is the graph of a differentiable function y equal to f of x is, and we have a few statements, a few definitions here. So concave up on an open interval I if f is increasing, f prime is increasing on I. And because of something we now know, this is the same thing as f double prime is greater than 0 on I, right? If f prime is increasing, that means its derivative, so the second derivative overall, is positive. And that's our definition of concave up. For concave down, we have a very similar definition. And that is on an open interval I, the function y equals f of x is concave down on an open interval I if f prime is decreasing on I. And again, what does that mean? That means f double prime is less than 0 on that interval I. All right, and so we have another definition I want to put down here. We'll see what all of this means via a picture in just a moment, but another quick definition, and that is a point where concavity changes is called a point of inflection if the function is differentiable there. All right. And then real quick, let's draw a picture. So in general, concave down looks like this. So we can think of it as a cup open downward. Concave up is like a cup open upward, so the water would stay in the cup. And a point of inflection is when we switch from concave up to concave down or concave down to concave up. One example from concave down to concave up would be something like this, like the y equals x cubed graph. Or y equals negative x cubed, where we switch from concave up to concave down. So these are both points of inflection. All right. And real quick, let's write down some example sketches. All right, we've talked about concave up and concave down now, and in previous videos we've talked about increasing and decreasing. So in general, if we have a function on a certain interval that is increasing and concave down, we get something like this. So this is increasing and concave down. Increasing and concave up would look like this. If we have an interval that is decreasing and concave down, we get something that looks like this. And if we have an interval that is decreasing and concave up, we get this. And so each of those would be, again, if we have this certain pair, any of these pairs of descriptions of the graph on a certain interval, then this is what they look like. We have one more theorem that we want to talk about before I end this video. So we're going to suppose f double prime is continuous on an open interval that contains C, then a few things might happen. If f prime of C is 0, in other words, we have a critical point, C is a critical point or a critical value on the function. Oops, I did not mean a comma there. And f double prime of C is less than 0, then f attains a local max or maximum at x equals C. We'll see this via a picture in just a moment. But I want to finish writing out this theorem. If f prime of C is equal to 0 and f double prime of C is greater than 0, then f attains a local minimum, minimum, well, let's just try writing that again, minimum at x equals C. And finally, if f prime of C is equal to 0 and f double prime of C is equal to 0 as well, then we learn nothing. Then the test fails. And by what do I mean by the test fails? I mean we learn nothing from checking these two things about our critical point C. Real quick, let's take a look at what all of this means via some pictures. Right? If we have a critical point and f double prime of C is less than 0, in other words, our function is concave down, so it's concave down, and we have a critical point there, then this is a maximum, right? That's what we've said here in this statement up here. If f prime of C is 0 and f double prime of C is greater than 0, that means the function is concave up there. That means we have a minimum. If f prime of C is equal to 0 and f double prime of C is equal to 0, then the test fails. We don't know. Maybe it's a maximum, maybe it's a minimum, maybe it's a point of inflection. We won't know. But in these first two cases, this gives us a lot of information and gives us another way to tell if our point is a local maximum or a local minimum. And that's a pretty powerful thing to be able to tell about a graph. And so that's very handy. All right, that'll end this first video for this section.